Day to all of you. So we're already in the 8th chapter of the Operating Systems lecture series. So chapter 8 is all about deadlocks. I've already mentioning in the previous lessons of the examples, real-world examples of deadlocks. So as I've said, it has its own dedicated chapter. So what are you waiting for? So let's start our lesson for chapter 8. So again, chapter 8 is all about deadlocks. So the contents of this chapter are, we have the system model, deadlock in multi-threaded applications, deadlock characterization, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock detection, and recovery from deadlock. And then the following are the chapter objectives. First is illustrate how deadlock can occur when mutex locks are used. Define the 4 necessary conditions that characterize deadlock. Identify a deadlock situation in the resource allocation graph. Evaluate the 4 different approaches for preventing deadlocks. Apply the banker's algorithm for deadlock avoidance. Apply the deadlock detection algorithm. And evaluate approaches for recovering from deadlock. So the system model. So system consists of resources. So these are resource types. So it is has a notation of R sub 1, R sub 2, until R sub m. So the example of resource types that is available in a computer system are the CPU cycles, memory space, and input-output devices. So for these resource types, so R sub I has W sub I instances. Example, in a computer system, we have I/O devices, its instances, or the number of existing I/O devices is equal to 5. So that's already an example of the W sub I instances. So each process utilizes a resource as follows. So for a process to use a certain type of resource, it should request for that resource. And after the request is granted for that resource, the process can already use that particular resource type. And then after the process has executed, it should release the resources that it's allocated to that particular process. So deadlock in a multi-threaded application. So assuming that we have 2 mutex locks that is created and initialized. So this is the 2 mutex locks and this is their initializing command. So for the first mutex and the second mutex lock. And then we have a code here in which, let's read the comment. So thread underscore 1 runs in this function. And then we have another code for thread 2 runs in this function. As we can see that the 2 threads has access to the to both of the mutex locks. So we have first and second mutex locks. So actually with this example, there is deadlock. So what if thread 1 has access for has already acquired the first mutex locks and thread 2 acquired the second mutex lock, but both of the threads need these 2 mutex locks to execute, or it will be used by the thread. So because of that situation, the thread 1 acquires the first mutex, and then the thread number 2 acquires the second mutex, and then they both need those mutex locks. So this is already a classic example of a deadlock. So deadlock is possible, as I've said, if thread 1 acquires first underscore mutex and thread 2 acquires second underscore mutex, as I've said. Thread 1 then waits for the second underscore mutex and thread 2 waits for first underscore mutex. As I've said with the example of 2 students, and then the resource, they're going to have a drawing session, and then you have a pencil and paper. And then what if student A has acquired the pencil and the student B has acquired the paper? So there is deadlock because no one will give in. For example, since student A already has the pencil, he or she will wait for the paper. While the student B, since the student B has already acquired the paper, he or she will wait for the release of the pencil. So this example of a deadlock, so it's very simple, 2 threads and then 2 resources. So it can be illustrated with a resource allocation graph. So this is the illustration for the first mutex. It is already acquired by thread number 1, and then the second mutex is already acquired by thread number 2, and thread number 1 waits for the release of the second mutex, while the thread 2 also waits for the release of the first mutex. So that is already a deadlock. Both are waiting who will release the particular resource. Okay, so deadlock characterization. So deadlock can arise if 4 conditions hold simultaneously. So these are the 4 conditions, and it is end. All of them should occur all at the same time. So first is we have the mutual exclusion. So only one process at a time can use a resource. And then we also have hold and wait. So for the number of process in using the resource, so a process holding at least one resource is waiting to acquire additional resources held by other processes. It means that at least one of the process is waiting. For example, the process has already acquired its resources, of course, but it's not yet enough, and it's waiting for to acquire additional resources held by other processes. And then next is we have the no preemption. A resource can be released only voluntarily by the process holding it after that process has completed its task. So it means that the release of the resources will only be possible if the process holding that resource has already finished its execution. And then we also have the circular weight. There exists a set of from p sub 0 to p sub n of waiting processes such that p sub 0 is waiting for a resource that is held by p sub 1, while p sub 1 is waiting for a resource that is held by p sub 2, and then that will go on until p sub n minus 1, and then p sub n minus 1 is waiting for a resource that is held by p sub n, and p sub n is waiting for a resource that is held by p sub 0. So these processes are waiting in a cycle. So as you can see, the maximum number of process, so for example, we have p sub n, is also waiting for a resource that is held by p sub 0. So actually, the fourth condition, this will really determine if there is a deadlock because of the circular wait. So we have a resource allocation graph. So this shows graphically to easily understand if there is a deadlock or not in a situation of processes requesting for a particular resource. So a resource allocation graph is a set of vertices V and a set of edges E. So V is partitioned into two types. So we have P from P sub 1 to P sub n. These are the set consisting of all the processes in the system. And then we have R from R sub 1 to R sub m as its notation, the set consisting of all resource types in the system. So we have two edges. So request edge is a directed edge from P sub I going to P going to R. If the arrow is from P going to R, it is a request edge, meaning the process has not yet acquired that particular resource and requests for that particular resource. While the assignment edge is a directed edge, so it's the opposite of request edge. So from R going to P. So if the arrow is from the resource going to P, it means that the process has already acquired the said resource. So that's why it is called assignment edge. So we have an example of a resource allocation graph. So from the right of our slide. So we have, so let's just enumerate. So one instance of R1, so this is the resource R1, only one resource for R1. And then two instances of R2, so this is R2, it has two instances. And then one instance of R3, so one instance only. And then three instances of R4. So as you can see, no, okay, this T here is thread. Okay, sometimes it is process and sometimes it can be a thread. So that's why it is T sub 1. So as you can see here, for resource 4, no thread is requesting for its resources. So we have an illustration here. So T sub 1, so we have resource 2 is assigned to T sub 1, meaning thread 1 holds an instance of R sub 2, and we have also an arrow going from T sub 1 to R sub 1, meaning that T sub 1 requests for another resource of R sub 1, or rather waiting for an instance of R sub 1. And then T sub 2, so for T sub 2, so it holds one instance of R sub 1. As you can see here for the assignment edge of R sub 1 going to T sub 2. And then one instance of R sub 2, so it also has acquired the resource number 2. So it is assigned also to T sub 2, and it also waits for the instance of R sub 3. And then T sub 3 holds one instance of R sub 3. Okay, for this resource allocation graph, so let's use the 4 conditions that is stated again. So let's go back. We have the mutual exclusion, hold and wait, no preemption, and circular wait. Okay, for mutual exclusion, so it is said here, only one process at a time can use a resource. So of course, one instance of resource assigned to a uh, thread or a process. And then hold and wait. So is there at least one process or thread that is holding a particular resource and then waiting for another resource that is held by another process? So we have that instances for T sub 1. It already has R sub 2 but it's waiting for R sub 1, which is held by T sub 2. And T sub 2 already has R sub 1 and R sub 2 as its resource, and it's waiting for instance of R sub 3, which is held by T sub 3. Okay, next is we have no preemption. So it is said that resources can only be released if a particular process or thread has finished its execution. So of course, they haven't finished the execution. So of course, they will not release these resources. And then the last one is circular wait. As we can see, it should be that T sub 1 is waiting for a resource that is held by T sub 2. So we have this instance that is R sub 1. And then is T sub 2 has waiting for a resource that is held by T sub 3. So actually we can see that in here. So is T sub 3 waiting for a resource that is held by T sub 1? Actually, for T sub 3, it does not. So can we conclude that is there a deadlock? Is the setup of the threads here has a deadlock? Actually, there is no deadlock because it does not have a circular wait, because it should have been if T sub 3 has an arrow going to R sub 2, then there is a possibility of deadlock, because it really has a possibility of deadlock because T sub 3's resources is waiting for the resource that is held by T sub 1. So for this particular example, there is no deadlock because the circular wait here is false, because it means that all processes, or rather threads. Okay, so we have a resource allocation graph with a deadlock. So this is a modification of the previous resource allocation graph. So as I've already said, this will have a deadlock because T sub 3 needs a resource that is held by T sub 1. So it already has a circular wait. So let's check. So again, mutual exclusion. So a process or thread should hold process one at a time. So we have that. And then they cannot, for example, if this one instance is already assigned to R sub 2, they cannot share. So that is the meaning of mutual exclusion. Then we also have hold and wait. T sub 1, T sub 2, and T sub 3 have these conditions that they already have a process waiting for the process that is held by rather waiting for a resource that is held by the other process. And then no preemption, there is no release again of resources unless the threads or processes has finished its execution. And circular wait, so T sub 1 needs a resource that is held by T sub 2, and then T sub 2 needs a resource that is held by T sub 3, then T sub 3 needs a resource that is held by T sub 1. So it's already a circular wait. So this definitely has a deadlock. Okay, next is we have graph with a cycle but no deadlock. So, okay, so let's check again the 4 characteristics of a deadlock. Mutual exclusion. So each of the resource is assigned to only one thread. So that is why, so R sub 1 is assigned to T sub 2, another instance of R sub 1 is assigned to T sub 3, and then R sub 2 is assigned to T sub 1, and another instance of R sub 2 is assigned to T sub 4. So that is already mutual exclusion. Then next is we have hold and wait. So does T sub 1 already has resources, of course R sub 2, and then T sub 1 is waiting for the resources that is held by other threads or processes. So R sub 1 is needed by T sub 1, it is held by T sub 2 and T sub 3. And also, T sub 3 already has a resource of R sub 1, and it needs additional resources, R sub 2, which is held by T sub 1 and then T sub 4. So it also has a hold and wait. And next is no preemption. So again, for no preemption, that the processes and threads will not release its resources allocated as long as they are not yet finished with their execution. So that is no preemption. And then we have the last, circular wait. So circular wait, okay, does T sub 1 needed a resource that is held by T sub 2? Yes. But does T sub 2 wants a resource that is held by T sub 3? Actually, it's not true because it only needs one resource from R sub 1. Does T sub 3 holds a resource held by T sub 4? Yes. But T sub 4 does need a resource that is held by T sub 1? Actually, no. So, though this example has a cycle, as you can see here for the T sub 1, T sub 3, but it does not have a deadlock because it does not satisfy the requirement of deadlock characterization, which is circular wait. And it has no also deadlock, since if T sub 2 and T sub 4 is finished its execution, then T sub 1 will acquire the resource that is released by T sub 2, and the resource released by T sub 4 will be acquired by T sub 3. So there is no deadlock. So this example, there is no deadlock, even though there is a cycle. So basic facts. So if graph contains no cycles, definitely there is no deadlock. So if graph contains a cycle, so as you can see, though in the example there is a cycle, but there is no deadlock because it does not satisfy the 4 deadlock conditions for the deadlock. So okay, then if a graph contains a cycle, if only one instance per resource type, then deadlock. So specifically, if the resource type has only one instance, then definitely there is a deadlock. So for this example, since the resource type has 2 instances, so if T sub 2 and T sub 4 is already finished its execution, then they don't need to wait for the resource. It will be allocated to the processes or threads that needed that particular resource. Then if several instances per resource type, there is a possibility of deadlock. Possibility, but not definitely there is already a deadlock. Because again, in the example that is illustrated here, that though there is a cycle, but there is no deadlock. So next is we have methods for handling deadlocks. So ensure that the system will never enter a deadlock state. So we have this deadlock prevention and deadlock avoidance. So allow the system to enter a deadlock state and then recover. So that is also another method for handling deadlock. And then ignore the problem and pretend that deadlocks never occur in the system. So first is we have the deadlock prevention. So invalidate one of the four necessary conditions for deadlock. So this is the only way for deadlock prevention. So mutual exclusion, not required for shareable resources such as read-only files, must hold for non-shareable resources. So next is we have hold and wait, must guarantee that whenever a process requests a resource, it does not hold any other resources. So for hold and wait, so if you're going to request a particular resource, you have to make sure that this process does not have acquired already additional resources. So require process to request and be allocated all its resources before it begins execution. So, or allow process to request resources only when the process has none allocated to it. So, it's like hold and wait is, for example, if you're going to request a resource, you have to wait for them to, for example, you need 3 types of resource. So, before you begin, you should be sure that these 3 resource types is already complete. If it's not complete, then you cannot progress for the execution and wait for that resource. So, um, take it or leave it. So if you're going to request, make sure that it is already complete and you can request all of them, not by chance, not just one resource type. And then the problem here with hold and wait is we have low resource utilization because you have to wait for you to complete your resources for you to start your execution. And then starvation is possible. What if there are other higher priority processes that needs that particular resource? And then for the no preemption, if a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. For example, that's already also related to the hold and wait. For example, you already have the resource, and since the resource that for example, you have one resource that is held by another process, since you cannot start your execution because you're still waiting for that particular resource, what is to be done is you have to release all of your acquired resources so others can use it, the other processes. So preempted resources are added to the list of resources for which the process is waiting, and then process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. So for again related to hold and wait, the process before it starts the execution, it should have completed its resource without waiting for other resource that is held by other processes. And then we have circular wait, impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. So that is for the deadlock prevention. So next is we have the circular wait. So invalidating the circular wait condition is the most common. So that is why I told you in the previous slide that circular wait, this really determines if the system is in a deadlock state. Then what we're going to do, simply assign each resource, such as mutex lacks a unique number. Then resources must be acquired in order. So for example is if first mutex is equal to 1 and second underscore mutex is equal to 5. So this is the code for the previous slide. So it should be changed. Okay? So that to avoid the circular wait and of course the deadlock. Okay, another one aside from deadlock prevention is also deadlock avoidance. So for deadlock prevention, there is a saying that, for example, in a sick person, it's like that prevention is better than cure. So for this type is we have the deadlock avoidance. The only difference with deadlock prevention is that, so for deadlock avoidance, it requires that the system has some additional a priori information available. So, a prior information that is needed for the system to avoid the deadlock. So, simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. And then resource allocation state is defined by the number of available and allocated resources and the maximum demands of the processes. So we have safe state. So when a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. So the system is in safe state if there exists a sequence from P sub 1 to P sub n of all the processes in the system such that for each P sub I, the resources that P sub I can still request can be satisfied by currently available resources plus resources held by all the P sub j with j is less than I. So that is, if P sub I resource needs are not immediately available, then P sub I can wait until all P sub j have finished. Then when P sub j is finished, P sub I can obtain needed resources, execute, return allocated resources, and terminate. And then when P sub I terminates, P sub I plus 1 can obtain its needed resources and so on. So this idea of safe state can be illustrated and what we're going to study for an algorithm that will be discussed in the next slides. So again, basic facts. If a system is in safe state, definitely there are no deadlocks. If a system is in unsafe state, there is a possibility of deadlock. Possibility. It's not that if it is unsafe, then it is already a deadlock. No, it's only a possibility. So avoidance ensure that a system will never enter an unsafe state. So we have an illustration here that of course if it is in a safe state there is no deadlock. Then if there is an unsafe state, it means that it has a possibility of a deadlock, and definitely deadlock is an unsafe state, but not the other way around. Okay, we have avoidance algorithms that we're going to be presented here in the presentation. So single instance of a resource type is we have to use a resource allocation graph. And then for multiple instances of a resource type, yeah, you have to use the banker's algorithm, which is devised by Dijkstra. So for one instance of resource type is we have the resource allocation graphs scheme. We have a claim edge. We have P sub I going to R sub j. So they have the same direction of request edge. Indicated that the process P sub j may request R sub j represented by a dashed line. So the difference between the claim edge and the request edge is that claim edge is a broken line and the sentence here is may request. There is a possibility that this process may request for that resource. So, claim edge converts to request edge when a process requests a resource. And then request edge converted to an assignment edge when the resource is allocated to the process. And then when a process is released by when a resource is released by a process, assignment edge reconverts to a claim edge. So resources must be claimed a priori in the system. So this is an example of a resource allocation graph. So this is the claim edge. So T sub 1 and T sub 2 may request a resource of R sub 2. And of course, so T sub 1, resource 1 is assigned to T sub 1, and then T sub 2 has no resources assigned to it, and it's requesting for an instance of R sub 1. So this is already an unsafe state in resource allocation graph. Why? Because as you can see here, T sub 2 has already the resource 2, assignment edge. And then T sub 2 needs the resource R sub 1, which is held by T sub 1. And then since this is a claim edge, so this is already an unsafe state because once this becomes a request edge, this becomes a solid black line, then it has already a deadlock because, of course, so for mutual exclusion, so one resource is held by process one at a time, and then hold and wait. So these two resources, specifically if this become a request edge, they hold resources, and then they are waiting for a resource that is held by the other process. And then no preemption, of course, they will not release the resources held if they are not finished with their execution. And we have the circular wait because T sub 1 needs a process that is a resource that is held by T sub 2, and vice versa, that T sub 2 needs a resource that is held by T sub 1. So this is already unsafe because once again, if this becomes a request edge, then it is already a deadlock. A deadlock exists. So the resource allocation graph algorithm, suppose that process P sub I requests a resource R sub j. The request can be granted only if converting the request edge to an assignment edge does not result in the formation of a cycle in the resource allocation graph. So, again, resource allocation graph is used for single instance of resources. What if there are multiple instances of resources? We cannot use the resource allocation graph, or rather, it will be more complicated. So what we're going to use is the banker's algorithm. So each process must a priori claim maximum use. So the system must already have the information, what is the maximum needed resources by each of the processes in the system. So when a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. So the data structures for the banker's algorithm, so that why is it called banker's algorithm? Because it's like you're borrowing the resource, and then it's like the resource is like money. You're going to borrow and then you're going to return it after a finite amount of time. So let n is equal to the number of processes and m number of resource types. So we have available. This is vector of length m. If available is equal to k, there are k instances of resource type R sub j available. Then max is n by m matrix, so it looks like a table. So if max is equal to k, then process P sub I may request at most k instances of resource type R sub j. Next is allocation. It's also a matrix, an m by m matrix. If allocation is equal to k, then P sub I is currently allocated k instances of R sub j. And then need, n by m matrix also. If need is equal to k, then P sub I may need k more instances of R sub j to complete its task. So the formula to get the matrix for need is equal to maximum minus allocation. So the safety algorithm for banker's algorithm, so let work and finish be vectors of length m and n respectively. So initialize, work is equal to available, then finish is equal to false for I is equal to 0 up to n minus 1. Find an I such that both finish is equal to false and then need sub I is less than or equal to work. If no such I exists, go to step 4. So if there exists, then work is equal to work plus allocation, finish is equal to true, then go to step 2. You're going to repeat it until you completed the sequence. And then if finish is equivalent to true for all I, then the system is in a safe state. So what does this algorithm mean? If you have a number of processes, and then you're going to find a sequence of processes in which all the process will finish its execution. So if the process finish, all the processes finish its execution, then the system is in a safe state. So for the resource request algorithm for process P sub I, so request sub I is equal to the request vector for process P sub I. If request is equal to k, then process P sub I wants k instances of resource type R sub j. So if request sub I is less than or equal to need, go to step 2. Otherwise, raise error condition since process has exceeded its maximum claim. So, if the request still fits, is less than the need, then you could proceed to step 2. But if not, then there is an error that the request is larger than the available resources at that moment. And then if request sub I is less than or equal to available, go to step 3. Otherwise, P sub I must wait since resources are not available. Pretend to allocate requested resources to P sub I by modifying the state as follows. So we're going to modify available is equal to available minus request. Allocation is equal to allocation plus request. And then need sub I is equal to need sub I minus request. If safe, the resources are allocated to P sub I, if of course if it's still available. If unsafe, P sub I must wait and the old resource allocation state is restored. So we have an example here of a banker's algorithm. So we have 5 processes from P sub 0 to P sub 4. And then we have 3 resource types. For resource type, so the total of 10 instances. And then B is a total of 5 instances. And C is a total of 7 instances. So this is the snapshot at time T sub 0. Okay, I have to be clear from here, from this example. Do not consider this as numbers. For example, 753, 322, 902, 222, 433. No. Since there is an ABC here, it means that, for example, for the allocation, for P sub 2, it means that 3 resources are assigned to P sub 2 for A, and then B, it does not need any resource type B. And then P sub 2 has already acquired 2 instances of resource C. So that is the meaning of this numbers. You should never consider them as a number 753, as I've said. So you should deal with them as individual. Okay? Because for the banker's algorithm, you're going to add or subtract not as a the 3 digits, but you have to separate them. Okay, so I'll give a separate video to illustrate the banker's algorithm here, because actually it's a relatively long process, because you're going to subtract the needed resources, and then you're going to return after the process has already finished its execution. You have to return all the resource that this particular process has used. So the content of the matrix need is defined as max allocation. You're going to derive the matrix need, which is max minus allocation. So max minus allocation, so you're going to subtract from A to A, B to B, then C to C. And max, of course, it should be max minus allocation. After subtracting the max minus allocation per process, this is the result. So by means of the need, so the system is in a safe state since the sequence, so we have this P sub 1, P sub 3, P sub 4, P sub 2, P sub 0 satisfies safety criteria. So again, I'm going to show you how does this sequence happened. So why is the sequence like that? So it is derived from of course the banker's algorithm, from its algorithm. So as you can remember, this is the algorithm for that. Okay, again, I'll provide a separate video for the illustration of the banker's algorithm that is given here in the slide presentation. So since for this example, so it is in a safe state. What if P sub 1 requests for additional resources, one resource type for one resource for A, then it does not need any resource from B, and 2 instances of resource C. So as you can see, what happened? So what happened here is that, as you can see, P sub 1 is 200 since it requested plus 102. Okay, since it has requested 102, you have, okay, 102, you have to add that. So 1 plus 2 is equal to 3, then still 0, and then 2 plus 0 is equal to 2. So that's why the new allocated resource is 302. Okay, but before you add that allocation, you have to check first if 102 fits here. So 102, it fits because it has still available resource for 3 for A, and then B is also 3, and then C is also 2. So we have to subtract 102. So this will be 230. As you can see with our example here. So that's why this becomes 230, and then after subtracting the request from the available, you have to add here in P sub 1. So that's why it became 302. So check that request is less than or equal available. That is, so it is possible. So that's why we already subtracted. Then executing safety algorithm shows that the sequence, so again, by using again the banker's algorithm, so it satisfies the safety requirements. So the question now here, if there is additional request for this P sub 4, additional resources, A is 3, B is 3 also, and it does not need any resource from C. So again, I'll provide this. Actually, the answer here is it cannot be granted because there is not enough resource available. Because 330, and you can already see here in the available. Okay, of course, check for C because it does not need any resources from C. And B fits because the available resource is 3. But the problem here is resource A. Since the available is 2, this is already what? 3. It exceeds the available. So, P4 requests for 3 instances of resource A, and there's only 2 instances of resource A. So, you can already answer. But again, I'll also provide it in the additional video for this one. So, another question is, can request for 020 by P sub 0 be granted? So, we're going to have 020. So, but before that, so this is already, the P sub 1 is already requested 102. So, actually, um, it still fits. So, we're going to subtract. So, 0 to 0. So, subtract. So, we have 0, 1, 2. This is the available resource. So, it's still less than the available, so the request. So, but the answer is this. If you're going to, again, use the banker's algorithm, the answer will be, though the resources requested by P sub 0 can be granted because it fits the available A, B, and C. Okay, but the system is in unsafe state because there is no sequence of the processes that satisfies the safety criteria. If you're going to use the banker's algorithm, you cannot produce a sequence that satisfies the safety criteria. You can only allocate the resource for P sub 0, but you cannot continue its process because it is already unsafe. So again, I'll provide an additional video so that you can see why requesting additional resources from P sub 0 will leave the system in unsafe state. Okay, next is we have the deadlock detection. So allow system to enter deadlock state. And then we also have the detection algorithm and recovery scheme. So for the single instance of each resource type, so we have this maintain wait for graph. So nodes are processes for P sub I to P sub j if P sub I is waiting for P sub j. Periodically invoke an algorithm that searches for a cycle in the graph. If there is a cycle, there exists a deadlock, of course. And then an algorithm to detect a cycle in a graph requires an order of n squared operations where n is the number of vertices in the graph. So a cycle, if all the processes are involved, that is the what holds true for deadlock to occur. Okay, so this is the comparison between a resource allocation graph and the wait for graph. So this is the resource allocation graph. So we have the resources. So the only difference for the wait for graph is you have to remove the resources and redirect the arrows. So for example, T sub 1. T sub 1 needs a resource R sub 1 that is held by T sub 2. So just remove R sub 1, and then since R sub 1 is assigned to T sub 2, then connect T sub 1 to T sub 2. And then another one, T sub 2. So this is already okay. T sub 2 needs a resource that is held, resource 3 that is held by T sub 5. So let's just redirect it. And then next is we have T sub 3. So T sub 2 also. So T sub 2 needs a resource 4 that is held by T sub 3. So just remove resource 4 and then redirect it to T sub 3. And then T sub 3 needs a resource that is held by T sub 4. So we have this one. And then T sub 4 needs a resource that is held by T sub 1. So, okay. Just remove the resources. So, this is the wait for graph. Okay. Then also T sub 2 needs a resource that is held by T sub 4. So, that is the wait for graph. You can derive a wait for graph corresponding to its resource allocation graph. Okay, next is what we have. We have several instances of a resource type. So available, a vector of length m indicates the number of available resources of each type. And allocation is n by m matrix defines the number of resources of each type currently allocated to each process. And then request is n by m matrix indicates the current request of each process. If request ij is equal to k, then process p sub I is requesting k more instances of resource type rj. So the detection algorithm, so let work and finish be vectors of length m and m respectively. So initialize, work is equals available, for I is equal to 1 to n. If allocation is not allocation sub I is not equal to 0, then finish is equal to false, otherwise finish is equal to true. Find an index I such that both is finish is equivalent to false and request sub I is less than or equal to work. If no such I exists, go to step 4. So for step 3, is work is equal to work plus allocation, finish is equal to 2, then go to step 2. Actually, detection algorithm is similar to banker's algorithm. The only difference is that you can see in our example, I'll show you the difference between banker's algorithm and detection algorithm. But their way of borrowing resources and returning all the resources that the process or the threads is used is just the same with banker's algorithm. So next step 4, finish is equivalent to false for some I is less than or equal to I is less than equal to n, then the system is in a deadlock state. Moreover, if finish is equivalent to false, then P sub I is deadlocked. So this algorithm requires an order of O, M times n squared operations to detect whether the system is in a deadlock state. Okay, this is an example of detection algorithm. So, 5 processes again from P sub 0 to P sub 4. Then 3 resource types. So, A has 7 instances, B is a total of 2 instances, and C has a total of 6 instances. So, this is the snapshot. So, the difference between Banker's algorithm, so they have the same allocation matrix and available vector. The only difference is that for Banker's algorithm, uh, the given in a Banker's algorithm is the max matrix, while for the detection algorithm is we have request. So for this snapshot, so sequence P sub 0, P sub 2, P sub 3, P sub 1, and P sub 4 will result in finish I is equal true for all I. Again, I'm going to provide an additional video for you to see how does this sequence why is this the sequence like this. It's of course it's by using again the detection algorithm that is stated in here for you to better understand. Okay, next, what if P sub 2 requests an additional resource of type C? So previously, the request, it does not have any requests for any of the resources, but now it requests for an additional instance of type C. So that's why P sub 2 becomes 001. So what is the state of the system? So actually, can reclaim resources held by process P sub 0, but insufficient resources to fulfill other processes or requests. So since it only executed P sub 0, it only finished its execution, and then the next processes did not continue its execution. So deadlock exists consisting of processes P sub 1, P sub 2, P sub 3, and P sub 4. Again, I'm going to show you how does this happen by an additional video. Okay, we have detection algorithm usage. When and how often to invoke depends on how often a deadlock is likely to occur and how many processes will need to be rolled back. So one for each disjoint cycle. If detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we would not be able to tell which of the many deadlock processes caused the deadlock. So, what are the ways to recover from deadlock? So, first is process termination. So, how does it be implemented in the computer system? So, abort all deadlock processes, or abort one process at a time until the deadlock cycle is eliminated. In which order should we choose to abort? First is the priority of the process, how long process has computed and how much longer to completion, and resources the process has used, resources that the process needs to complete, how many processes will need to be terminated, and is the process interactive or batch. Okay, another one is resource preemption. So you have to select a victim. This is to minimize the cost, or rollback, return to some safe state, restart process for that state, and starvation. Same process may always be picked as victim, include number of rollback in cost factor. So this is already the ways on how to avoid deadlocks. So we have Banker's algorithm and deadlock detection algorithm. So again, I will provide additional video for you to illustrate how does this sequence produced. So if you do have any questions, so please feel free to comment below, and please don't forget to like my YouTube channel. So I hope that you've learned something from this lesson all about deadlocks. So again, thank you very much. Good day and stay safe.